All right, welcome back to K11 Tech University. In our last explainer, we dove into combinatorial algorithms and saw how, pretty quickly, you get this explosion of possibilities. And that leads us right to the huge challenge we're going to tackle today, a question that really changes the game when it comes to solving tough problems.
And that question, right there, is everything. How do we find the answer we're looking for without wasting a ton of time, computing power, and energy going down paths that are just dead ends? You know, this is really the difference between an algorithm that's technically correct and an algorithm that's actually useful in the real world.
Okay, so let's get right into it. The core problem we're up against is that these algorithms face a search space that is just mind-bogglingly huge. Even if you have a perfect way to check every single option, you eventually run headfirst into a very hard, very real wall.
I mean, think about it. What good is an algorithm that's going to take the age of the universe to finish? For all practical purposes, that's not a working algorithm at all. It's a broken one. And brute force approaches fall into this trap all the time.
And it's not just about waiting around forever. There's the raw computational cost. The amount of memory and CPU power you'd need to even think about every possibility can be absolutely astronomical, way more than any computer could ever handle.
So here's the bottom line. For any real problem, whether you're talking about logistics or finance or AI, just trying everything is not a strategy. It's a non-starter, a dead end. We have to be way smarter than that.
And you might think, well, let's just get faster computers. But that's just a band-aid. The real, elegant, and scalable solution isn't about hardware at all. It's algorithmic. And it's built around this beautiful, powerful idea called pruning. So, what is pruning? Well, here's the key. It's not about searching faster. It's about searching less. It's a strategy of making intelligent and sometimes kind of ruthless eliminations. It's like a sculptor looking at a block of marble. The genius is in knowing exactly what to chip away.
You know, what I love about this definition is how active and decisive it is. We are eliminating paths. We are stopping exploration. We are avoiding work. It's all about making smart, confident decisions as early as you possibly can to just chop off entire branches of possibilities that you know for a fact are worthless.
Seriously, if you only take one single thing away from this explainer, let it be this. This is the entire philosophy right here, in just 6 words. It completely changes your approach from a blind, brute force march into a guided, purposeful, and intelligent exploration.
Okay, so that's the big idea, the philosophy, but how do we actually do it? Let's open up the algorithmic toolbox and look at a few techniques that are incredibly common and super effective.
The simplest and most direct way to prune is something called an early exit. So imagine you're looking for the cheapest flight. You find one for, say, $300. Great. Now you start looking at another route, and after just the first 2 legs, the cost is already $350. Are you going to keep exploring that route? Of course not. You stop, right then and there, you exit early. That one tiny check might have just saved you from exploring millions of useless combinations. It's a simple idea with a massive, massive impact. Now let's build on that. Your absolute best friend in this whole process is constraints. These are the rules of the game that you define up front. Things like a maximum budget, a weight limit, or maybe rules about what parts are compatible with each other. By checking these rules early, you give your algorithm the power to throw out invalid options before it even wastes a single cycle on them. This doesn't just save you a little time, we're talking orders of magnitude.
Okay, a more formal strategy that uses these exact ideas is called branch and bound. It might sound a bit complex, but the intuition behind it is actually beautiful. First, you branch out and start exploring. As you do, you keep track of the best answer you found so far. That's your bound. And here's the magic step. Anytime you start down a new path that you know, even in a best-case scenario, can't possibly beat your current best, you just abandon it. You prune that entire branch. It's a disciplined way of applying that cheapest flight logic, and you see it everywhere from AI planning to scheduling problems.
And all of this brings us to what I think is the most important part of this whole discussion. Learning these techniques isn't just about adding a new tool to your coding toolkit. It's about a fundamental shift in how you think about solving problems. This is where algorithmic thinking really starts to mature.
I mean, just look at the difference here. You're moving from this novice mindset of let's just try everything and see what happens to a disciplined, expert mindset that asks, how can I eliminate everything that's impossible as fast as possible? It's a huge shift from being exhaustive to being intelligently selective.
And that's the core lesson right there. The most brilliant, the most effective algorithms in the world, they aren't the ones that just churn through data the fastest. They're the ones that are clever enough to know which data they can confidently and completely ignore.
So let's talk about the real-world stakes. Why does this matter so much? Because when you're building a complex system,
This isn't just a nice little optimization. It is, and I mean this literally, a matter of survival. And this strategy is absolutely everywhere once you know to look for it. It's how your GPS finds the fastest route without checking every single road on the planet. It prunes routes that are clearly going in the wrong direction. It's how modern AI systems can find the best settings for a model without trying trillions of combinations. This is the engine that powers things like backtracking, search trees, and so much more. The difference is just it's night and day. Without pruning, that exponential growth we talked about always wins. Your system will collapse. Time just explodes. But with pruning, problems that seemed impossible suddenly become solvable. Complexity is tamed, and your algorithms can actually scale to solve real, meaningful problems.
So let's be really clear about this. We have to stop thinking of pruning as just some optional optimization. For any system that has to deal with a large space of possibilities, it's a fundamental, non-negotiable survival strategy. Period.
So where are we headed next? Well, in our next explainer, we're going to formalize all of these ideas by looking at a classic algorithmic pattern that is the perfect embodiment of this kind of thinking: backtracking. It's basically the art of structured search with constraints. It is pruning in action.
I want to leave you with this final thought, because I think it captures everything we've talked about today. The real art of designing great algorithms isn't about raw power or searching harder. It's about the wisdom, the elegance, and the discipline of knowing when to stop.
This is K11 Tech University. Thanks so much for joining us. We'll see you in the next one.